Most people use electricity daily, but not many understand the basic principles of electric fields. But before tackling electric fields, let's start small and talk about charged particles. Protons have a positive charge and are surrounded by negative electrons in an atom. The amount of electrons or protons in an atom can create a positive or negative charge for that particle depending on how many they are. Charge uses coulombs as a unit, and a single electron or proton has a charge of plus or minus 1.60 times 10 to the negative 19th coulombs. When two objects are rubbed together, some of the electrons transfer over to one object, giving it a negative charge and leaving the other with a positive charge. This is called the triboelectric effect. It is important to note that the total charge, meaning the total number of coulombs in the system, is constant in any process, according to the law of the conservation of charge. The transfer of electrons creates static electricity, which means the surface of an object is charged. Some objects tend to lose electrons and become positive, like glass and hair, while others tend to gain electrons and become negative, like plastic products like Teflon and amber. Once charged, opposite charges attract each other, and like charges repel each other, since most systems want to return to a neutral and balanced state, and desire to balance each other out with the opposite force. Items can become charged by contact, as seen earlier by rubbing stuff, or by induction, which is when a charged object draws the opposite charge toward it and repels the like charge to the other side of the object, as seen in the image. These charged items give off electric fields that pull in oppositely charged particles and push away like particles. Now for some electric field examples. In example A, a positive field pushes a positive charge to the left, since they repel each other since they're the same charge. When another positive field is added on the left in example B, the charged point is caught in the middle with no movement. There is no force pulling in either direction, since they're both repelling in opposite directions, and it's caught with no velocity. However, if we move to example C and a negative field is placed above the positive charge, it moves upward to approach the oppositely charged field, which attracts it, and the two other forces below it cancel out and have no effect. We can find the exact strength of the electric field using this information using the equation E equals K times Q over R squared. In this equation, E represents the strength of the electrical field, K represents Coulomb's constant, which is equal to 8.99 times 10 to the 9th. This constant is used in equations about electric field as determined by Coulomb, who is a unit is named after. Q is the charge of the point. In this case, it's the blue point that we saw in our earlier graph that was being pushed around by the electric fields. And R is the distance from the center of the field, which would be the distance the center that blue point is from the center of any of the fields that is acting upon it. So, in summary, for electric fields, the transfer of electrons to certain materials creates charges, and then those charges create electric fields that exert force on positive or negative charges of other objects. The direction of the fields is determined by the charges of it and how opposite particles attract, and the repulsion of like particles.